Okay, welcome back. This video is primarily for page 5 of the chapter 2 notes for AP Stats, but I am currently sitting on page 4, your reading guide, just to introduce the topic. Section 2.2, of course, is normal distributions. Normal distributions are one of the most prevalent distributions in the world that we live in. Okay, they show up in nature. Most measures of physical species, whether it's weights or lengths or things like that, tend to be this normal distribution for reasons we can't even necessarily fully explain. It shows up in manufacturing. It's all over the place. So obviously, in a statistics course, we're going to come across distributions of data that are normal or approximately normal. And therefore, it is in our interest to be pretty familiar with calculations. We want to have ways to find locations, specifically within a normal distribution. We want to know various properties. Okay. The most famous property of a normal distribution is the bell shape of its density curve. So most of your data is clustered sort of around the mean in the middle. Then you've got symmetric tails off to either side. In any population, you're going to have some individuals that are significantly taller than average, some that are shorter than average, but it's about the same spread in either direction. Having said that, we don't want to assume that any bell-shaped graph is a normal distribution. As you're going to see later in the course, there are other classifications of distributions that are bell-shaped and yet decidedly not normal. So the question is, what else is it beyond the bell shape that makes something a normal distribution? And one of the key things with that is what's called the empirical rule. So this is a rule that applies to any normal distribution, okay? Various normal distributions might have different means and standard deviations, but what links them all together is the percentage of data that falls within one standard deviation of the mean, and then 2 deviations, and then 3. And these 3 numbers we should memorize. They are not on a formula sheet in this class. 68, 95, 99.7. So 68% of observations in any normal distribution are within one standard deviation of the mean. But that includes either direction. So really, as we'll see in a second, it's like 34% out of that 68% is to the right. The other 34% is to the left of the mean. Okay. And I'm scrolling down. It's also worth noting, and we talked about this in the last video, it's possible to take a distribution, whether it's normal or otherwise, and convert every value into a z-score using a z-score formula. And if you were to do that with the normal distribution, we convert all the data into its z-scores, you will find that the new mean is 0, and the size of the standard deviation is now 1. We talked about those values being fairly important when you standardize a distribution. So if you ever see a reference to standard normal distribution with a capital S, you automatically know the mean, you know the standard deviation. All right, I think I'm ready to jump on down to page 5. There's really just one example here, and then I'm going to start getting into some calculator tricks that help us with normal distributions. Example 2.2.1, it is widely accepted that the typical human body temperature is 98.6 degrees Fahrenheit. However, this value is based on data collected in 1851. Modern studies suggest typical human body temperature has actually decreased over time. I've got a link to an article if you want to read some more about that. But a more recent study found a mean temperature of 97.9 with a standard deviation of 0.65 degrees. Assuming that the distribution is approximately normal, we are going to sketch the density curve for a distribution of body temperature based on the recent study. We're ignoring our 98.6 and we're going with the more recent data. This is a type of graph you may have to create from time to time. So that's why I'm showing you how to do it. Okay. As far as the curve itself, I'm just drawing kind of an informal bell shape. We don't honestly refer to the shape itself. We're more interested in some of the markings below it. Okay. But what I've done here, I'm going to actually start in the center. Right underneath the peak, right under the center of that bell shape, I'm putting the mean of 97.9. Okay. And then both to the right and the left from there, I'm marking some scale tick marks on the axis. I'm going to go 1, 2, 3 in either direction. And these marks are supposed to refer to standard deviations, meaning if I start in the center and move one notch to the right, I've moved exactly one standard deviation. Well, standard deviation here is 0.65. So mathematically, I'm doing 97.9 plus 0.65. And I've got the temperature that lines up with being exactly one deviation higher than the mean. And I could add 0.65 again and again. I could start subtracting 0.65 on the other direction to get a collection of numbers that correspond with being 1 or 2 or 3 standard deviations to either side of the mean. In fact, you'll notice I've labeled these values with degrees Fahrenheit, but just below that, I'm converting them to their z-scores. You could plug every single one of these numbers into your z-score formula, and you'll get exactly -3, -2, -1, and so on up to 3. Now, the next thing I'm going to bring in here is the empirical rule from the reading guide. I'm going to start by looking one deviation away from the mean in either direction. I've got cut points for that. We know, this being a normal distribution, that 68% of all temperatures are going to live between those values. And more specifically, we break that 68% up into a 34% and a 34%. Okay. Now, I'm going to allow myself to move 2 deviations in either direction. And according to the empirical rule, these intervals within there have to hold 95% of all temperatures. But keep in mind, the 68% from earlier is already included in the 95. So if I want to figure out, where did this 13.5% come from? The calculation that I'm doing there is 95 minus the 68 that was already accounted for, and then divide that in half due to symmetry. And that's how I knew to put 13.5% within these subintervals. And of course, we're going to go one notch further in each direction. Allow yourself to go as far as 3 deviations to either side. Okay, so that takes us now, we're ranging from 95.95 degrees all the way up to 99.85. 99.7% of temperatures are going to fall within that range. So to figure out these minuscule percentages here, I'm doing 99.7 minus the 95 that's already been planned out, and then dividing by 2 again to split that according to symmetry, half on each side. So what we're seeing here is the vast majority of observations in a normal distribution are going to be within 3 deviations of the mean. Even being within 2 deviations is 95%. So it's actually somewhat rare to be more than 2 deviations above or below a mean. And yet it's also possible to be even more extreme than that. There's 0.3% that's going to be super extreme. I'm cutting that 0.3 in half to get my 0.15s on either side. Okay, there isn't officially any cap on how far up and below you can go. It's just extremely rare to have data falling out there. It would almost certainly be outliers. Now I've constructed this graph, and the reason we have it is it's going to help us with some of the questions below. Okay. You're also going to see me starting to use some new notation, and the notation that I'm showing you is not optional. When you show work for normal calculations and eventually some other calculations in this course, we're going to be using the notation that you're going to be seeing below in a moment. And to help with that notation, you might also notice that I've officially defined a variable here. When I use the letter X throughout my work below, we know that X is going to represent body temperatures in degrees Fahrenheit. Okay. So for part B, with all the given information above and with our chart here, can we determine what percent of temperatures, human body temperatures, would be greater than 98.55? And of course, this question is actually pretty simple now that we've got our well-labeled graph with some percentages measured within the different regions under the curve. All I need to do is find 98.5 and then add up all the percentages for regions that are greater than that. And that's my answer. But there's a fairly specific way to explain that. So here's the work that I've been talking about. I'm using a capital P followed by an inequality in parentheses. We will see this notation throughout the course. You can think of it as P for proportion. Eventually, we'll see that it's probability in some contexts. What's nice is its P words are the words that we're usually using this notation for. So the way to read this is quite literally what proportion of body temperatures, that's the X, are greater than 98.55. And if you've added up the percents, we've got an answer. It's about 16%. Eventually, I might ask you to write a sentence conclusion in context, but we're going to wait until maybe the next lesson to introduce that part of it. So for now, this is what an answer is going to look like. Part C, what percent of temperatures would be between 97.25 and 99.2? Again, we see those cut points conveniently located on the scale. We just need to add up the percentages within, and we have to show this P notation, capital P, whoops. And this time we've got a compound inequality because I'm interested in temperatures that are between two specific cutoffs. But we're going to add up those numbers and we get about 81.5%. All right. Part D is not a calculation. Instead, it's asking you to consider, again, what is the story behind some of the numbers and stats that we're seeing? What might be a plausible explanation for this observed decline in human body temperature over time? If you want to pause the video and think about it, come up with a hypothesis or two, go for it. Some possible answers, however, well, maybe we've got improved measurement techniques. Whatever we were using to measure temperature in 1851 was possibly not as accurate as what we've got nowadays. That's one plausible explanation. I don't know to what extent that's true, but it's plausible. Additionally, perhaps there's just better overall health of the population. We've got improved science and medicine and technology. People might not be quite as beat up and sick as they were back in the 1850s. And of course, that would result in less overall inflammation within your body, which is going to bring your temperature down. That's another possible answer. All right, so that's our example for empirical rule calculations, but I would hope that you've got a lingering question after seeing this example, because it was ever so convenient that questions B and C asked you about percentages directly above or below the cut points that we've established from empirical rule. But not every question is going to be so convenient. What if I wanted to know what percent of humans actually have a body temperature less than 98.6? Okay. There's a cut point that's relatively close, but it's not 98.6, right? It's actually going to be somewhat rare that the questions asked involve numbers exactly 1, 2, or 3 deviations away from the mean. So ultimately, this technique is not the most useful one. We need another way to perform normal distribution calculations. And luckily for us, you have a couple options at your disposal. It is possible to use your calculator. There are calculations in the Stats app that handle normal probabilities and proportions. And believe it or not, if you don't have the Stats app, your calculator dies during the AP test, God forbid, the formula sheet has ways to help you as well. So we're going to take a look at both of those things. Honestly, you'll use the calculator most of the time, but you definitely want to know how to use the formula sheet as a backup plan. Okay, so the chart at the bottom of this page is introducing you to some of the methodology here. First thing to notice is there's going to be two different varieties of questions that are commonly asked with normal distributions. The ones higher up on the page correspond to this first row. These are questions where you're tasked with finding the proportion or percent of observations above or below or between specified locations on your distribution. Okay. And if we're going to use a calculator for that type of question, there's something called normal CDF that I'll show you in a moment here. Okay. Actually, let's do it right now. I'll do an example before we jump into the other type of problem. I'm going to turn on my calculator just a second here. I'm going to switch over to my camera. Okay. So, unsurprisingly, we're going to head to the Stats app. And once you're in there, we're going to actually go to F5. And there it is, the fourth choice down, normal CDF. Go ahead and hit enter, and you will see that there are 4 inputs required here. Okay, lower value, upper value, and then we see the symbols for mean and standard deviation of a population. Okay. If I want to find the percentage of humans with a body temperature below 98.6, okay, well, if you think about that, we're below 98.6, then 98.6 is like the upper bound of temperatures that I'm asking about. So we'd put in 98.6 as an upper value. There is no lower value. There's no cap on the low end. I'm willing to go as low as we can go. If that's the case, I think you can actually leave lower value empty and it'll work, but we can also put in negative infinity. That was a negative sign followed by infinity, which lives on the catalog button. I have to hit diamond and then catalog. I want to put in that negative infinity. And next, I want to put in the mean and the standard deviation from the prompt. So I believe it was 97.9 as a mean. And then we had the 0.65 as a standard deviation. Okay, now that we've got our numbers plugged in, we're just hitting enter. Actually, I might need to press that twice. And the result at the top is the proportion, or you could convert to a percent, of human temperatures that are actually less than 98.6. Okay, pretty easy to use. I'm going to go back in right away. The normal CDF. If you had two actual cutoffs, maybe I want to know what percent of temperatures are between 97.9. Actually, that's the mean. I don't want to use that exactly. But 97.7 and 98.6. I could easily put in both a lower and upper value. I can hit enter a couple times and get a result. It's also worth knowing that we could input z-scores instead of raw data. Okay, maybe I want to know what percent of temperatures are within 1.5 deviation of the mean. I can directly put in z-scores as long as I then convert the mean and standard deviation to be the standard normal standardized distribution of z-scores. And of course, when you do this, whoop, technical difficulty there for a second. Go back. As I was saying, when you do that, that means you're putting in a 0 for standard deviation and a 1 for the mean. Okay, and I'm just going to repeat that because it is pretty important and will come up. If we put in z-score boundaries instead of raw data, we always use 0 for the mean and 1 for the standard deviation. And hit enter a couple times. There it is. Okay. Well, let's go back to the notes. I've got the steps, the rough steps here for normal CDF. Okay. Well, what if your calculator dies? All right. There is a way to use a table in your formula sheet. I believe it's called Table A. We'll look at it in a second. But what you can do, you can calculate a z-score for one of your boundary locations, round it to the nearest hundredth, and then there's going to be a way to look the z-score up on the formula sheet in a table such that the table reports back to you the proportion of a distribution that lives below your z-score. Now, you don't always want information about below a location. You might want information about what percent is above, but that's pretty easy to do. You just go with 1 minus whatever answer you're getting. But let me show you the table first. Flip over here. Yeah, it's about halfway through the formula sheet. It's called Table A, Standard Normal Probabilities. Okay. And it allows you, like I said, you have to calculate a z-score first. All right. And then you're going to look up your z-score at least out to the 10th place. You're going to look that up in the first column. You'll notice all the z-scores on this page are negative, but don't worry, there's a second page that has, actually the third page, that has positives as well. Okay. And then once you've got the z-score out to the 10th place, you're going to go over to a column that's determined by the 100th place. So if I have a z-score of 1.01 that corresponds to some location, and I want to find what percent of my temperatures are below a z-score of 1.01, I'm going to find 1.0, and then I'm going to go over to the 0.01, and there's your answer. Okay. Now I repeat, you have to convert your location to a z-score first. There's obviously not a temperature of 98.6 in here, but you could calculate the z-score for 98.6. I don't know exactly what it is, but if we go back to our notes, it would be a little bit higher than 1, right? But you could find that z-score and then find it in the table and go over. Just remember, these are areas below. If I wanted to find the percent of my data that is above a z-score of 1.01, I have to go with 1 minus whatever number I'm seeing here. Okay. Now, there is an entirely opposite sort of problem we might have to calculate as well. Everything we've seen so far involved finding a proportion above or below or between locations that we already know. What if we want to go backwards? What if I want to find a location when I'm given a specified proportion above or below? For example, what if I wanted to figure out percentiles? What is the 90th percentile of temperature? What's the 40th percentile? Okay. I'm going to show you how to do that on the calculator real quick. Flip back over. Once again, we're heading to F5. If I'm going backwards with my calculation, I hope it would make sense that this choice inverse might be appropriate. This is the inverse operation of what we first looked at. So I'm choosing inverse, and the very first option within the submenu is inverse normal. We're going to choose inverse normal. And there are now 3 inputs required. Okay. First one says area. This can be confusing because what you have to put in here, the way it's programmed, it's similar to the paper table or the formula sheet table in that it wants an area below a location of interest. It doesn't say that here, but that's how it's programmed, which works out great for percentile. If I want to find the 90th percentile of my temperatures, I could type in 0.9. Notice I have to do this as a decimal. I'm not going to literally type in 90. I'm going to type in 0.9 for the area below, as in 9/10 of the area, 9/10 of the observations are below me. And then I have to put in my mean and deviation. You'll notice that it currently says 0 and 1. You could actually leave the 0 and the 1 if you want to get back a z-score. It'll give you a z-score. And there may be cases where you want the z-score. But for right here, right now, I'd rather get my answer back in terms of actual degrees Fahrenheit. So I'm going to change my mean back to 97.9. I'm going to change my standard deviation back to 0.65. And when I hit enter, I'm going to get the temperature that reflects the 90th percentile. There it is. Okay. 98.733. This is an inverse normal calculation is what it's called. You start with some knowledge of a percent, either below or above, and you can find a location. Just be careful with it. Like I already said, we want areas below. You might see questions on a test that ask about area above, but it's simple, right? If it says find the location such that 60% is above, well, then you can easily determine that if there's 60% above, there must be 40% below. So you can kind of find the area below on your own. But what if your calculator breaks down? I'm going to show you how to use the table backwards. Use the given info to choose a known proportion below a desired location. We're going to find that proportion in the interior. We're going to start on the inside of the table and work our way out to find a z-score. Okay. Flip over here. If I wanted to find the 90th percentile of temperature, I'm starting on the inside. I'm looking for as close as I can get to 0.9. Luckily, these are in numerical order. To go down, down, down. Okay. Looks like the closest one is right here, 0.8997. And what I learn is that I've got an 0.8 in my column. I've got a 1.2 in the row. So the approximate z-score is 1.28. Okay. Now you're not quite done, because then you have to figure out, okay, how do I convert from a z-score back to regular data? But that's doable if you use your z-score formula. You plug in your 1.28 right here. You already know the mean and the standard deviation for the temperatures. You could solve for x to then get your final answer. So yeah, it's not quite as quick as the calculator, but it'll do in a pinch. We're going to see more practice with these calculations in the next lesson. I'm not sure if it'll be a video or in class, but stay tuned on that. Thanks for watching. Shoot me an email if you have any questions.